This is a basic integration table. If you come over to handouts, you'll see other integration tables. If you come here, I've put a whole bunch up here that are the common integration tables that you're going to encounter. And ideally, you don't have to use an integration table. Most of these you should have memorized already. So when we look at this, you really should have certainly from 10 and above, you should have those memorized really well by now. And then we've got our three inverse trig function ones. So we've got the one that integrates to inverse sine, secant, and tangent. So these we're going to see a lot moving forward, especially that one, and then this one second most. This one we'll see occasionally, but the top two blue ones we'll see a fair amount, especially inverse tangent. So these should be ones that if you don't have memorized, you need to have them memorized pretty darn soon. When we get into a topic called trigonometric substitution down here in 8.4, we'll come up with a way that actually makes coming up with those three formulas pretty straightforward. So, but it's a very good idea, especially to have those two memorized, because you're going to see them enough that it's worth it. Now, the integral of tangent and the integral of cotangent, you should already know how to do those too. We did those as hyperbolics. Those are in what we have called in this class log form. And remember that if we have the integral of tangent of x dx, that is in log form when we rewrite it as its common ratio. The common ratio for tangent is sine over cosine. And remember, log form, super important. It's in log form if the denominator's derivative is the numerator. Then it's in log form. And you're looking at that, and that's very close to log form. What's the derivative of cosine?
Negative sine.
Negative sine. So if we just multiply by 1, now it's in log form. You can always multiply by 1. Negative 1 times negative 1 is 1. Now it's in log form because the denominator's derivative is the numerator. So then our answer is the natural log absolute value of the denominator. So we have that. And you're looking up there and you're saying, well, that's not quite there yet. It's like, yeah, it's not quite the same. Well, we could take this coefficient of negative 1 and we could, have it fly up into the exponent position of the argument, and then 1 over cosine of secant. So you could write it like that. Either way is fine, though. You could absolutely write it this way or that. Doesn't matter. Both of those are fine. And, of course, the AX, that's just a reverse chain rule. If this happens to be a 2x, like we've done a lot in Unit 1, if that was a 2x, we just divide by 2, right? We divide by the derivative of the substitution. And similarly for cotangent. So these two, also not too crazy. Now these ones are a little crazier. We are going to see this one a fair amount right there, that the integral of secant is what it is there. So let me say this. When we look at our trig functions, we know that sine and cosine essentially integrate to each other. There's a minus sign in one of them. But they essentially integrate to each other, sine and cosine. If you look at the other 4, if you look at tangent, cotangent, secant, or cosecant, they all integrate to a log function. Right? All 4 of them integrate to a log function. And every time you see something that integrates to a log function, you should sort of back up and say, oh, I bet we could write the integral in log form. If it integrates to a log, there must be some manipulation that could happen to put the integral in log form. And now this is not going to be obvious how to put this in log form, but if someone says, what is the integral of secant of x? We don't care if there's an ax in there because we know we would just divide by the a in the end. If it was secant of 4x, we'd have a division by 4 in the end by reverse chain rule. But if we want to rewrite this, our trick that we've learned over and over is multiply by 1. Somehow multiply by 1 to change the form. It's kind of like unit conversion, right? You're just multiplying by 1. 12 inches divided by 1 foot is 1. If you can multiply by 1 in the right form, that's the ticket. And it's not obvious here, but once you see it a couple of times, it should become more and more obvious. So first off, somebody tell me what the derivative of secant is. The derivative of secant is secant times tangent. And that's how I remember this multiplication trick. So derivative of secant is secant times tangent. And I want to multiply by 1. And I'm not going to multiply by secant times tangent. I just use that as a memory trick that if I multiply by secant plus tangent, top and bottom, that's just 1. Notice what happens. Notice what happens. When we multiply numerator and denominator by secant plus tangent and then distribute the secant across that numerator there, right? So we're just distributing this across, secant times secant, secant times tangent. And then I'm just going to rewrite the denominator. I'm just going to change the order. Order doesn't matter when you're adding. Doesn't matter which is first, which is second. I'm just going to change the order. Because now it's obvious. The derivative of the denominator is the derivative of the sum. Take the derivative of each term. What's the derivative of tangent? Secant squared. What's the derivative of secant? Secant tangent. Now it's in log form. We're done. As soon as we get an integrand that is in log form, which means derivative dot denominator is numerator, then you're done. Then it's natural log, absolute value of the denominator. Normally they write it as secant plus tangent instead of tangent plus secant. So I'll just rewrite it like that. And that's how you integrate secant. You're going to see the integral of secant a fair amount of times. You should get to the point where you don't even have to do that. You just write it down because it comes up so much. Yeah?
Do you think, like, just copying these equal one basic approaches and putting them on flashcards and memorizing them is a good idea?
Yes, absolutely. I think it's a great idea.
Good thing.
What better way to go to bed for the next month? Right?
Just copying them down.
Maybe throw
Yeah.
chemistry in there too.
Yeah, you could throw in a little bit of chemistry too. If you want some, some dementors flying into your dreams. Okay, so these basic ones, practice them, make sure that get them down, because you have to have them down. If you can't do your basic integrals, the rest is going to be such a nightmare. Again, it's like trying to factor when you don't know your multiplication tables. It's like, you can't do it. You have to have a basic foundation of memorized stuff so that you can operate efficiently. You can't always go back to the beginning. It's kind of like going to the grocery store. If you had to go to a new grocery store every freaking time you went shopping, it's like, okay, today I'm going to go to Safeway. Today I'm going to go to Publix. Today I'm going to go to King Soopers. As you go to the same grocery store again and again, you get efficient. You know where everything is. You go in order. It's that type of thing. If you don't develop a foundation, you can't just always start from square zero every single time. You don't have time, and it's frustrating. So you've got to get the basic level of memorization down. And most of the time, that memorization just comes from doing enough problems. You get that muscle memory where it's like, oh yeah, like the power reduction identities, you should have those memorized by now because we've done them enough. So this is just kind of a review of some different integration techniques that we're going to learn. We've talked about this already. If we're integrating sine squared, anytime you have a sine squared or a cosine squared, not for the other trig function squared, only sine squared and cosine squared, you have to reduce the power. And so you need a way to memorize this, so we've talked about it already. So both of them have a 1 minus cosine of 2 theta. And somehow you have to remember which one has the minus, and so you can think of sin as negative, whatever you want to do. Somehow you have to remember that the minus goes with sine. And once you have that power reduced, then it's just a matter of using reverse chain rule with that cosine of 2 theta. This is a linear angle right there. It's linear. And so anytime we have a linear substitution, all we have to do is integrate the trig function, leave the angle alone, and then divide by the derivative of the angle. So there's our antiderivative. So, power reduction, again, it's only, you can distribute the half if you want, it's only good for sine squared and cosine squared. So let me just point out one algebraic thing here. Do you see how the half is factored out of just these two terms here, but it's not factored out of the c? Usually, this would be the preferred way to write the answer. Of course, I wouldn't take off for that, but just when you're thinking about what's the best, this is the preferred way to write it. If you're factoring is only useful if you can factor it out of everything, because then you can set it to 0 and figure out what the zeros of that expression are. But if you can't factor it out of everything, that doesn't give us any benefit there. So usually this would be the preferred way to present that answer. Okay, let's look at this this other one here with cosine. Let's see. Are you going to let me scroll without that? So let's take a look at this one. So here, it's still a power reduction thing. We have to reduce that power. So is it clear how this power reduces? This is going to be the integral. You can put the over 2 out in front. That's usually a good practice. And so that's going to be 1 plus cosine of 2 theta. And so what's that 2 theta going to be?
6 theta.
Yeah. So every time we reduce the power, we double the angle. That's what that formula is saying. The power on cosine is being reduced from a 2 to a 1, but the angle is being doubled. So reduce the power, double the angle. So if we double this angle, we get a cosine of 6 theta. And then again, we can integrate term by term. So we're going to get theta plus integral of cosine of sine 6 theta divided by 6 plus c. And distributing the half would make the most sense here. So and you could write this as 1/12 or sine of 6 theta over 12, doesn't matter. So that would be our...
So it doubles the denominator as well? Goes from 2 to 6?
Well, when we distribute this half, if this half is out front, we
No,
have
I'm
to...
talking about, yeah.
So that half is getting distributed over to the 6.
But with the original, the sine of 6 theta over 6?
Yep.
Okay.
So you take the derivative of the inside and divide
Yeah,
by
so
it.
it is 6, and then you take the derivative of that, so it is 6.
So you
Okay.
take the derivative of that, that's why we divide by the 6. But then if we distribute that half, that 2 in the denominator is going to combine with the other denominator of 6. Correctamundo. Okay, so RCR. So we just did an RCR. Let's just refresh. We talked a lot about this already. This is how you would do it in Calc 1 in the last couple weeks of the semester. You say, oh, substitution, it's the only technique I know. So you're going to let u equal the exponent. You're going to take the derivative of both sides. You're going to isolate the dx. And then you're finally going to get back to the integral. So this integral is going to be equal to the integral of e to the u, and then dx is du over -4. And then you would factor out the -4. And then you would do the integration. And then you would back substitute. Is that correct math? Of course it's correct math. Is that efficient math? Not even close. Not even close. By this stage of Calc 2 this semester, you should be able to write this answer down instantaneously using reverse chain rule. The integral of an exponential is itself. First and foremost, it is itself. It is the one function that has that cool property. Its derivative and integral starts off as itself. And if we're integrating, then we just divide by the derivative of the exponent. That's it, right? Done, one step. Instantaneous. 1, 2, 3, 4, 5, 6 steps. That is not how you want to be doing your math. That is not an efficient way to integrate when you have a linear substitution. So when we have, again, reverse chain rule is when you have a linear substitution. So that is linear. All you do is divide by the derivative of the exponent. Reverse chain rule. Chain rule, if you were taking the derivative, you would multiply by the derivative of the exponent. So we call it reverse chain rule. Or I call it reverse chain rule. So, similarly down here, the integral of cosine is sine. Angle doesn't change. And then we divide by 5. So that is our reverse chain rule. And this reminds me of question 1 on the exam. You had to integrate sine of 2t. The integral of sine is cosine with a negative, and then we divide by 2. That's how you integrate. You could use substitution if you want, but again, that's inefficient, so we just do reverse chain rule. That's what it was on the first question on the exam. Integrate and then evaluate from 0 to pi. Okay, so this one. This one maybe is not as obvious. It's really obvious when you're dealing with angles and exponents that you can use the reverse chain rule. Really obvious. With angles and exponents, it's more obvious. But it also works for roots. If we look at this root, that is linear. And if that is linear, we can use reverse chain rule. Reverse chain rule is a shortcut for linear substitutions, which are the most common. So here we would just take our base. Like, let's rewrite this so that we have the base. Let's just write it this way just to make it a little bit cleaner. So we have the base raised to a power. The base is linear. So we take our base and we do what we normally do with a polynomial. Add 1 to the exponent, divide by the new exponent. But then there's one more step. Divide by 4. So we're going to divide this all by 4 because that's the reverse chain rule. Could you use substitution? Of course. And then if we want to simplify this, we're going to have 2 divided by 12, which is 1 over 6. We can combine those constants out in front. And that'll be our antiderivative. More precisely, the family of antiderivatives. And we're thinking of that as a family of curves that all have the same. This family of curves all have this function as its derivative. So we're going to have a lot of little strategies here, and it's the only way is to do enough practice to sort of internalize them. One thing that you look at in this integrand, and it should jump right out at you, is that there's these negative exponents. Negative exponents, the first thing you want to do is get rid of them. Negative exponents are not useful when you're integrating. You want to get rid of them. And so we need to understand how to get rid of these negative exponents. And so to get rid of these negative exponents, what do? We multiply by 1. Multiplying by 1 is how you change the look of something without changing the value. Right? You change the look, you change how it is presented, but you're not changing the value of anything. So we want to multiply by 1. So we're going to multiply numerator and denominator by something to eliminate the negative exponent. And our basic rule of thumb, we know from algebra that if we have something like, let's suppose we have x to the negative 2, if we multiply that by x to the positive 2, what do we get? 1. Right? This is x to the 0. You have bases, the bases match, so you can add the exponents, and x to the 0 is 1. That's going to be our ticket. That is our strategy. So when we look over here, we're like, oh gosh, okay, well we need to multiply by something with the same base, and we want to have the exact opposite exponent. So if that's a negative z, we want to multiply by a positive z. So if we multiply numerator and denominator by e to the z, that will eliminate the negative exponent. Let's see. So in the numerator, we end up with e to the 3z. And in the denominator, this e to the z gets shared, right? It's got to go here and here. It's got to be shared. It's got to be distributed. So e to the z times e to the 2z is e to the 3z. E to the 3z minus 4 times, times 1, times e to the 0, times 1. Now, negative exponent's gone. So that's what we do. We multiply by 1 in a form that the exponents can combine to 0 so that you can eliminate the negative exponent. Now, when we look at that, what form is that almost in? It's almost in log form. The derivative of that denominator, derivative of negative 4 is 0. Derivative of e to the 3z is e to the 3z times 3. So what do? We force the numerator to look how we want it to look. But we can't just multiply by 3 there. We need to offset that. We need to multiply by 1. So 3 times a third is 1. Now it's in log form. Now it's in log form. We're golden. We can say, oh, this is 1/3 natural log absolute value of the denominator. So log form, again, we are going to see that ad nauseum. All right, now let's take a look at this crazy looking thing. Again, we see a negative exponent, so we know we need to multiply by 1 in a way to get those exponents to add up to 0. So what form of 1 should we multiply that's going to take care of both of those negative exponents simultaneously?
Y cubed.
Y cubed. We take the exponent that has a greater magnitude, and that's the one we're going to focus on. And so when we multiply by y cubed over y cubed, in the numerator we get y cubed. And in the denominator, we have to share. So this y cubed has to be shared between each term. What's y cubed times y to the negative 1?
Y squared.
Y squared. All right, we add the exponents. So 3 plus negative 1 is 2. So we end up with a y squared for that first multiplication. And plus 1. Perfect. Fancy. Now we're in another one of these miscellaneous situations. If you are in regular arithmetic, regular old arithmetic, what do you call a number that looks like this? What do you call that fraction?
Irrational. Improper.
Improper. Improper. Right? When you hear the word fraction, you think of part of a whole. Like 1/4 is a proper fraction. It's less than 1. 2/3 is less than 1, 4/5 is less than 1, 9/10 is less than 1. If it's top heavy, then it's improper. That's not really a fraction, right? It's more than 1. It's an improper fraction. And so you could write this as 4 plus 1/3. Right? You could divide the 3 in and write it that way, and back in arithmetic they don't want to they want to minimize the number of strokes used, so they don't put the plus. So 4 1/3. We have the same concept with rational expressions. So this rational expression, we have a polynomial up top that has degree 3. Down below we have a polynomial of degree 2. It's top heavy. There's more power up top than down below. So this is what they don't use the expression, but I would call this an improper fraction. It's an improper rational expression. And we do the same thing. Our strategy, if we have an improper fraction, is to do this, is to divide. So here's where you have to recall long division. Every algebra technique that you ever hated comes flying back in Calc 2. So we're going to have to do long division. So let's come over here. So we're going to take y squared plus 1, and we're going to divide it into that numerator. Bless you. So we do long division. So that goes in there, y times. We ask ourselves, what times y squared is going to match this? What times y squared gives us y cubed? So that gives us y cubed plus y. You have to have some decent mechanics here. Remember that you're subtracting this whole quantity from what's above it. So some people just go through and change the signs. That's a little, it's very hard if you end up making a mistake to go back and figure out what happened. I will always just put parentheses and the minus out in front so I can see what the original was. So if I come up with some mistake, I'm not trying to recreate what happened. And then we subtract. Y cubed minus y cubed is 0. And then up here, if you have to, you can put in a placeholder. There's no y's up here. So then you have 0y minus 1y, which is negative y. And as soon as this power is below that, you're done. Just like regular division. As soon as it's smaller, you're done. So what this tells us then is this. We can rewrite this as the quotient. That's what that's called, the quotient. And then we take, so this is called the quotient. This is called the remainder. And this is called the divisor. And so we take the remainder and put it over the divisor, just like we would do up there with numbers. So we take the remainder and we put it over the divisor. And that's exactly what we did up here. We divided the 3 into the 13. We got 4. That's the quotient. And there was 1 left over. 3 times 4 is 12. There's 1 left over. That's the remainder. And it goes over the divisor. Or denominator in that form. Same denominator and divisor, the same thing. So that's what we have. All right. And that can now be integrated almost immediately. The integral of y is obvious enough. That's y squared over 2. And what form is the second fraction, or the second term in? Log-ish. We have to do a little bit of massaging. The derivative of this denominator is 2y. The numerator is only y, so we need to put what we need. We give this a little bit of space in here. So we multiply by 2 in the numerator. Now it's in log form, but we have to offset that 2. We need to put a division by 2 out in front. So I'm going to write that like this. I'm going to put a 1/2 right there. So now it's in log form. So the minus 1/2 And then the log form tells us that we're going to get log, natural log. In math, whenever we say log, we mean natural log unless otherwise indicated. We'll get that. So there is our indefinite integral, aka family of antiderivatives. So lots of little kind of nuances, again, that only become more and more clear by practicing. Okay, so this is one that will drive you a little crazy because it's not something that we normally check for. You know, so that's kind of a new thing. Like when you see rational expressions and you're taking derivatives, it didn't matter if it was top-heavy, you just do the quotient rule. But now with integration, if it's top-heavy, it does matter. You need to do long division in order to break it into two parts. So another common technique is called fraction splitting. So fraction splitting is when you have more than one term up in the numerator and you have one term in the denominator and you're going to distribute it into the numerator. You're going to distribute that single denominator into each term in the numerator. So here we could rewrite this as the integral of 3x divided by square root 4 minus x squared. And say again? Oh, plus, yes. Plus 1 over the square root. So we're going to make two fractions out of the 1 and separate the 1 integral into 2. So we have that. Now the second integral, hopefully with more and more practice, you're going to start seeing it pretty quickly, is that's going to be an inverse sine. And we'll get into the weeds of why it's inverse sine and what the form of this has to be to give you inverse sine. We'll get to that when we get to trigonometric substitution. But for now, all we could do is use the table. Okay, what technique can we use for that first integral?
You could put it to negative x bar.
This was 13A on the exam.
Oh,
Substitution. Substitution. If you let u be this quantity, remember when we do use substitution, this is not in log form. This is the derivative of that square root. You'd have to pull down the half, subtract 1. That's definitely not the numerator. The numerator is way simpler than the derivative of a square root. But what's important when you do substitution, usually it's the exponent, the angle, what's inside the square root. But usually it's something that's sort of inside. But in order for substitution to work, the substitution of that amount, that quantity, has to be present. And it is here. If we take the derivative of a quadratic, we get a linear. And that's what the numerator is. It's linear. It doesn't match exactly negative 2x, but the nature of it is the same. They're both linear. So that means it's just a multiple of the derivative. So that's going to work really nicely for that one. So let's come over here, do our substitution. So if we let u equal 4 minus x squared, then du will be negative 2x dx. And we're just going to try to target this x dx part. You know, again, like sometimes to help me solve this, we'll try to force it to be a 3. Don't bother. We can pull the 3 out and match the x dx. So we can make this du over negative 2 is equal to x dx. So if we can match the x dx part, that's going to be good enough. So let's see. So we pull the 3 out. 3 is out in front. And then we have the integral. X dx becomes du over negative 2. So over negative 2 comes to the front. So now we've done the 3 in the x dx. Just like on the exam, this is square root of u, but it's in the denominator. And when you're integrating something in the denominator with a power, you just push it upstairs. So that's going to be u to the minus 1/2. So that's how this part's going to roll. Now this integral, we recognize that it's an inverse sine, and this has an a value of what? So if I look at this,
It's 2.
so the a value, so the first term here is considered a squared, so the a value is 2. So we need to have an inverse sine of x divided by 2 plus c. That makes sense to everybody? So there's no the coefficient is just 1. If you look at the inverse tangent and inverse secant, there's a 1 over a out in front. But for inverse sine, it's just inverse sine. There's no constant out in front, just a 1. So that is the integral of that one. And then we're almost done here. So this is going to be negative 3/2 to integrate a power, add 1, divide by the new exponent. So if we add 1, we get u to the 1/2. If you add 1, you don't get 3/2, you get 1/2. And if you divide by 1/2, that's the same as multiplying by 2. And then we still have the second part over here. And we just have one step left. We want to simplify and replace the u with 4 minus x squared. So there we have it. That is our indefinite integral family of antiderivatives. A lot of times we'll just call it the antiderivative. Sometimes you'll hear people say the general antiderivative. Okay, any questions on any of those steps? We had a few different things woven into that one. All right, let's do another long division one. So the first thing we notice here is it's a rational expression that's top-heavy. Whenever we have a top-heavy rational expression, an improper fraction, if you will, we need to do long division. Bless you. So the first thing I want to do, though, is rewrite this a little bit. It's easier to do long division when everything is in descending power, descending order. The powers are in descending order. So we're going to rewrite it like that. All right, you all try to do this long division. Let's go. College algebra. Long division. Hopefully it feels easier now than it did when you first learned it. Long division. Oh, Edgar. No, you can't, because when you have addition in between terms, you can't break apart addition like that. It's just like if you have square root of 2 terms, you can't break it apart. So this is sort of one term. We wish, right? Okay, so 3 people I barely recognized that came and took the exam. The 3 lowest scores, okay. Huh. Coming to class important. No wonder. Every semester there's 1 to 3 people think, yeah, I'll just watch the YouTube videos. Bad idea. The data is irrefutable. Best of intentions. Okay, so the long division, again, we ask ourselves, what multiplied by x squared is going to match this first term? Answer, negative x squared. That'll give us negative x to the fourth minus 4x squared. So I'm leaving a little bit of space up here. If you want to, you can put in a placeholder. You can put in a 0x squared there. You don't have to. Now with long division, the next step is subtracting. So I'll always put this minus sign out in front and parentheses around that whole quantity. You can just change the signs if you're super confident and you're good at it. So then we can think about distributing this minus. So it's going to be negative x to the fourth plus x to the fourth, which is 0. So 0x to the fourth. And then here we have 0 minus, so 0x squared plus 4x squared, that's 4x squared. This power is still not under that power, so we have to keep on going. And we draw the 6 down, drop the 6. And we don't need that 0 out in front, so let's get rid of it.
Plus 4.
So now we're going to add 4. We're asking ourselves what multiplied by x squared matches that 4x squared. So answer plus 4. So that's going to be 4x squared plus 16. And then once again, we are subtracting that quantity off. So 4x squared minus 4x squared is 0. 6 minus 16, negative 10. So that allows us to rewrite this. So first the quotient. The quotient is what's on top, so there's the quotient. Plus the remainder over the divisor. The remainder is negative 10. We'll pull that negative to the front, so that's negative 10 over x squared plus 4 dx. So that is the long division step, the wrong division step. So it's one of those things you just have to recognize, oh, the power up top's bigger, long divide, long divide. So then we can do our power rule, so negative x cubed divided by 3 plus 4x minus 10. And does anyone recognize that one? Inverse tangent. And what is the a value for this inverse tangent one? 2. And so for inverse tangent, there's going to be a 1 over a out in front, so 1 over 2. And then it's inverse tangent of x plus c. So the only thing we could do is simplify these coefficients to 5 right there. All right, any step there that we could pull over that inverse tangent in case that's not making 100% sense. So we have the inverse tangent integral. If we have dx over x squared plus a squared, that's going to be 1 over a times inverse tangent of x divided by
Yeah, x over 2.
x over 2. X divided by a. Yeah, I thought it was x divided by a plus c. All right, let's make that one not look like a mutant. And so this right here should be x over 2 in here. X over 2 inside. X over 2 for both those. So the inverse tan and inverse secant have this 1 over a and an x over a. Inverse sine has the x over a on the inside, but no 1 over a on the outside. All right, let's go ahead and take a 10-minute break, and then we'll be moving towards integration by parts, something everybody's been waiting to see. Continue to integrate. So yet another random one-off strategy. Most of our denominators have been 2 terms. If there was a square, there was no linear term. Now we have a trinomial down there. That trinomial is managed by another college algebra technique, completing the square. So completing the square. Also notice that we have a definite integral in this case, so integrating from 0 to 2.
Gotta love that.
Gotta love it. A little extra work just for practice. So we've got our x, I'll put it as x dx in the numerator. In the denominator, how do we complete the square?
Factor.
Mm,
Oh.
take the coefficient of x, divide by 2, and then square it. So divide by 2 and square. So in other words, if we take that 4, divide by 2 and square, we get a 4. So this would be a perfect square trinomial. X squared plus 4x plus 4. That's what we want. Perfect square trinomial. And so what we can think about doing is taking away from the 8. The constant in the denominator has to be an 8. Well, we need a 4 to pair off with these first 2 variable terms to create a perfect square trinomial. So we can just borrow those 4 from the 8, right? Just take those over. So now we have a perfect square trinomial that can factor. So that factoring is going to give us x plus 2 quantity squared plus 4. Yep, and the dx.
DX.
Yeah, dx is funny. It makes more sense conceptually to always have it out in the tail, like the integral and the dx, kind of like a sandwich. But we always try to shortcut it and minimize the number of strokes and minimize the space so we can throw it in the top if we want. Okay, so we have this now. It's looking better, but we still have some problems. Down here we have an x plus 2, so we might think about using substitution. That will get us somewhere for sure if we want to try substitution. If we want to, we don't quite have an inverse tangent thing set up, but it sort of is smelling a little bit inverse tangent-y. But we've got that numerator of x that doesn't, and there's no x up there. All right, so let's try substitution and see where it takes us. Let's see if that can shed some light. And this is integrating your trying stuff and seeing what sticks. So if we do that, we have that, du is dx. So let's just see if we get anywhere with this. If not, we'll try something else. Heck, black. If not, we'll try something else. Limits of integration would be 2 and 4. If we substitute the 2x values in. Now, we end up with this, u squared plus 4, and we have a du. But what about that x in the numerator? Exactly. So if we look up here, we can get this equation right here tells us how u and x are related. So we could just as easily isolate x as u minus 2 and replace the numerator x with u minus 2. Yep. Okay, so now we've converted all over to u. And we had a technique we've already used today that we could use again here.
sub again.
Let's not use U sub again. Not yet. Let's not do repeated U sub. But what did we do earlier? We
Split it.
split it. Break out the axe, the hatchet. Let's split it. So we're going to distribute that denominator into each term in the numerator. So we're going to make two integrals out of one. So we split, go that way, and then we're going to split it the other way. And I'm going to leave the 2 in the numerator. No, I'm not. I'm going to factor the 2 out of the numerator. So that's just du over u squared plus 4.
And you have the first tangent.
There's the inverse tangent. Lollygagging around, hiding. Okay, first integral. What form? Log-ish. We have to do a little massaging. Multiply by 1 in the form of 2 divided by 2. Now the first integral is in log form, the second's in inverse tangent form, so we are ready to roll. So we are going to have 1/2 natural log absolute value of the denominator. Don't really need the absolute values because it's positive, but we'll just put them anyway. All right, and we have a definite integral. We're going to have limits 2 to 4, but they're the same on both integrals, so we can just do one evaluation step. So everybody okay on that first integral? Log form, derivative of denominator is numerator, so it's natural log of the absolute value of the denominator. And then minus 2. I've had a lot of these a's that equal 2 today. So x squared plus 2 squared, so a is 2. So we have the negative 2 out in front, and then we have a 1 over a, so that's going to be a 1 over 2. And then we have inverse tangent of x divided by 2. U divided by 2, thank you. U divided by 2. And then our limits of integration are 2 and 4. So that integration, that evaluation is for everything. We can do this all at once. We see some cancellation right there. That makes life a little bit simpler. Those two will cancel out. So let's plug in the 4 across the board. Plugging in the 4 across the board. That's going to be 4 to the 4, which is 256, plus 4 is 260. So we're going to have 1/2 natural log 260 minus arctangent of 2.
I said 4 to the 4th, sorry.
4 to the 2, right? Not 4 to the 4.
Oh, why did I say 4 to the 4?
I don't know.
I don't know either.
So 6 to 20?
I don't even begin to understand why I thought it was 4 to the 4. So 4 squared is 16, that's 20. That's a little more manageable. 20. 4 squared. Who knows? Minus arctan, 4 divided by 2 is 2. I'm going to stick with that. Minus, drop in the 2, so 2 squared is 4, plus 4 is 8, so minus 1/2 natural log 8. Natural log 8. And then minus a minus is plus arctangent of 1. So we have a tiny bit of simplification that we can do here. Not a whole lot, but a tiny bit. So how about some log properties? That is going to be equal to, if we factor out the half, then we have log 20 minus log 8, which is log of not 12. Log property, difference of logs turns into
20 over 8.
20 over 8. Log of 20 divided by 8. Log property. Log of A minus log of B is log of A over B. Log of A minus log of B is log of A over B. Arctan of 2, is that a special angle? All arc functions are angles. Is that angle special? Do you know the angle with a tangent value of 2? No. No. The only special values we know for tangent, we know the tangent of 0 is 0, and we know that inverse tangent of 1 is pi over 4. Those are the only two we really identify. So inverse tangent of 1 is pi over 4. And then we can just simplify this a little bit, divide 4 into there and get a 5, divide 4 into there and get a 2, and that's about it.
And would you recommend putting the 2 into the exponent of the natural log or leaving it out?
Do this square root thing.
Yeah.
Turn that, doesn't matter.
Okay.
Yeah, you could
Either way.
if you wanted. Inverse tan of 2. This reminds me of a very cool equation. Seeing these inverse tangents. So check this equation out. Inverse tangent of 1 plus inverse tangent of 2 plus inverse tangent of 3. That is equal to pi. Arctan 1 plus arctan 2 plus arctan 3 is pi. And I claim that I can prove this to you by drawing. So I claim that I can prove this to you with this picture. I claim that I can draw 3 lines in there and to prove this. Arctan 1 plus arctan 2 plus arctan 3 is pi. So first off, anytime you see an arc function, you're thinking angle. So arctan of 1 is the angle that has a tangent of 1. Arctan of 2 is the angle with a tangent of 2. Arctan of 3 is the angle with a tangent of 3. Pi, if you're looking geometrically, visually, pi is a straight line. So if we draw this line right there, that angle right there is arctan of 1. Because those are all 1 by 1 blocks. That angle right there is arctan of 1. And if I draw this line right there, that forces this to be a right angle. And then the final line right here, this angle over here is arctan of 3. It is the angle that has a tangent of 3. The tangent of this angle is opposite, which is 3, over adjacent, which is 1. So that is arctan of 3. Arctan of 1 is this one. And then the one in the middle here, that is arctangent of 2. Because the tangent of this angle is 2 diagonals over 1 diagonal. So the arctangent of 2 is that middle angle there. So that proves it. Arctan 1 plus arctan 2 plus arctan 3 is pi. This angle down here is pi, right? Those 3 add up to a straight line, which makes it pi. There's a really cool math book called Proof by Picture. And it's this book of all these kind of interesting theorems where the proof is just a picture that you can interpret geometrically. It's kind of cool. So, anyone going out for tattoos this weekend? That's not a bad one. Arctan 1 plus arctan 2 plus arctan 3 is pi. Okay.
Can we use it on the test?
That? Sure. Not any tattoo,
Oh, okay.
but that tattoo.
Start getting the whole handout tattooed.
Yeah, get the unicircle right in your hand. Okay, so let's go with another miscellaneous rando technique. Conjugate multiplication. Zach?
I know, what do you feel that you found the test?
If you get that tattoo on your forehead, you can use it on the test.
Just walk up to the whiteboard and see the reflection.
Take his glasses off. You can do it? No? You're not going to take me up on it? Okay. I think that's a smart decision. Okay, so here's another technique. We know with trig functions, most of our important identities involve trig functions squared. All those Pythagorean identities, the trig functions are all squared. And this denominator has a trig function in it, but it's not squared. This fraction also has the unpleasant characteristic that the denominator is two terms and not one. When the denominator is one term and the numerator is multiple terms, you can split the fraction. But if the denominator is multiple terms, you can't do that. We can't split this fraction. You can only split if you have something that's going into parts of the numerator. So what we're going to do here is do conjugate multiplication, and this will have two effects. So if we multiply by the conjugate here, so 1 plus cosecant of theta over 1 plus cosecant of theta, this will have a couple of good end results. So first off, what it's going to do, the numerator is going to be two terms, and the denominator is eventually going to be one term, because that denominator is now an identity. 1 minus cosecant squared comes from a Pythagorean identity. If you cannot remember your identities, always go to the basic one, sine squared plus cosine squared is 1, and you can algebraically figure out the other two by dividing by sine squared or cosine squared. This, we want a cosecant squared, and 1 divided by sine squared is cosecant squared. So if we divide this all by sine squared, this will generate the identity we want. Sine squared over sine squared is 1. Cosine over sine is cotangent, then we're squaring it. And then 1 over sine is cosecant, so that's cosecant squared. So if we subtracted the cosecant squared to the left to generate exactly what we have over there, then we would have to subtract the cotangent squared to the other side. So that denominator can now turn into a single term, which is great because then we can split the fraction. When the denominator is a single term, you can split fractions. So let's see, what do we end up with? So 1 minus cosecant squared minus cotangent squared. I'm just going to factor the minus all the way out to the front. Seems like a hassle having it inside. So that's going to be cotangent squared d theta. All right, we're getting closer. Now we'll split the fraction. What is 1 over cotangent squared?
Tangent squared.
Tangent squared. Does that have an antiderivative? Close, but we're not quite there. That does not have an immediate antiderivative. We don't know a function that has tan squared as its derivative. We know a function that has secant squared as its derivative. What function has secant squared as its derivative? Tangent. And we could turn tangents into secants with another Pythagorean identity. So we're holding off on tangent squared for the moment. Now we've got this miserable thing, cosecant over cotangent. Cosecant over cotangent. All right, anytime we have those co-functions, if you don't have an immediate antiderivative, one generally good strategy is to turn them into sines and cosines. That's usually a good way to go. Because the co-functions are just much harder to work with. We're not as familiar with them. So let's get rid of them, turn them into sines and cosines, or something like that. So let's see. Cosecant is 1 over sine. cotangent, so cotangent in the denominator would be tangent in the numerator. And so we can think of this as tangent squared in the numerator, which is sine squared over cosine squared. Or you could think of this as cosine squared over sine squared, but it's being divided, so you have to flip it for multiplication. However you can conceptualize that is fine. Okay, so let's see where we're at. All right, so we have this minus sign out in front, still integral. So tan squared, let's rewrite that into secants. And here, so obviously we could come up here and divide by, what would we divide by if we want to get secants? If we divide by cosine squared, we'll get this. So instead of that, if we divide everything through by cosine squared, sine squared over cosine squared is tan squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. So you can subtract 1 from both sides here, and you're going to get tan squared of theta is secant squared minus 1.
We can do that.
We can do that. Now I'm going to show you a picture. This identity shows up a lot. That secant tangent identity shows up way more than the cosecant one. So I think it's very convenient to have a visual representation of that identity. And here is the visual representation of this identity, that if you can get this visual aid down, you will never think twice about this identity. So, if you take an angle in the unit circle, and let's just suppose I am at that angle, and you extend it, and then drop this down here. So there's theta, right there. And you create this interesting right triangle that is beyond the unit circle, but it's created in such a way that this horizontal distance right there is 1, right? It's a unit circle. Everyone with me? So all we did is extend the terminal ray until it's right above 1, 0 and drop it. Well, we have actually similar triangles here. If you look at if you look at this black triangle right here, that black triangle, I'm going to pull it out, that's the standard triangle that you're used to looking at, where the hypotenuse is 1, and the horizontal is cosine of theta, and the vertical is sine of theta, correct? Do you agree that the red and the black are similar? Similar triangles are angles that have triangles that have the same angles but different dimensions. So you agree the black and the red have to have the same angles. Right? Those have the same angles. And the property of similar triangles that I want you to think about is that rise over run is the same for both. Similar triangles have equal proportions. So the rise over the run for the red triangle has to match the rise over the run for the black triangle. What is rise over run for this black triangle?
Sine over cosine.
Which is
Tangent.
tangent. So now we look at the red triangle, and the red triangle has to have that same exact setup. So the red triangle, which has a base of 1, the rise over the run has to be tangent, but if the run is 1, what does the rise have to be?
Sine over cosine.
Tangent. It has to be tangent. Okay? So if vertical over horizontal is tangent, then vertical over horizontal has to be tangent. If horizontal is 1, then vertical has to be tangent. And that makes the hypotenuse secant because of the Pythagorean identity. So when we look here, this is tangent. That vertical rise right there is tangent. And the diagonal, the hypotenuse, is secant. And there is your identity. 1 plus tan squared is secant squared. You can see it really easily. This is very convenient way to think about the identity, because you can imagine as the angle is rotating towards pi over 2, you can see tangent getting bigger, right? As this angle rotates, the value of tangent's growing vertically there. And so that gives you a nice visual for tangent as it rotates to pi over 2. It becomes undefined at pi over 2. There is no triangle at pi over 2 anymore. So as you get closer to pi over 2, tangent gets enormous. But another feature here is that it's totally obvious that secant is always more than tangent. Right? Secant is the hypotenuse. Tangent is the vertical. So no matter how that angle rotates, that hypotenuse is always longer than that vertical side. So secant of theta is always more than tangent of theta. Okay, so that allows us then to say the following.
That's what you have to subtract.
So tan squared, we look at this, is going to be the hypotenuse squared minus 1, right there. So tan squared of secant squared minus 1. Secant squared of theta minus 1. And now over here, we can cancel out one sign. So that exponent is going to wipe that out. So we're going to have sine over cosine squared. And here's how I'm going to rewrite that. Sine over cosine squared. I'm going to rewrite that like this. I'm going to think of it as 1 over cosine multiplied by sine over cosine. So I'm going to think about that denominator of cosine squared and sort of split it into a product of two fractions. We are getting so close. All right, so this minus is still in front. We can now integrate that. We can integrate that. What's 1 over cosine? Secant. Sine over cosine is tangent. And do we have an antiderivative for sectan? Yes. Derivative of secant is sectan. Now we have antiderivatives for every term. Okay, so let's go. So we have minus 1 multiplied by all this stuff. Integral of secant squared is tangent, because derivative of tangent is secant squared. The integral of negative 1 is negative theta. And the integral of sectan is sec. Plus c. I have no memory of where we started. It seemed like it was a mile long ago. All right, there's no limits of integration. That's all we have. So the only step left is to distribute that minus sign. So we have minus tangent of theta plus theta minus secant of theta plus c. This is the antiderivative you've been looking for.
All right, we can go home.
Almost.
We have to integrate, never mind, don't listen to me.
Okay.
I thought this was the definite integral.
Yeah, that's what I was checking for. I couldn't remember where we started.
Will we ever do a double in the substitution?
Double sub?
Yeah.
Yeah.
Yay for rippy cases.
Soon. Oh, we're almost to integration by parts. We're almost to integration by parts. Integration by parts is so powerful. It's going to allow us to integrate all sorts of stuff. All right, so a couple more weirdos. This thing, why don't you all try this one? So let's go with this substitution and see if you can make that substitution work. So usually with substitution, we want it to be inside the square root, inside the angle, inside the exponent. We're going for what's inside this outer square root. So go ahead and see if you can make this substitution work. Some integrals you can do multiple ways. Let's see if this, let's see if you can make that one work. So this is kind of the first place where it sort of feels a little funky. The square root of u part's obvious, right? Because you're letting u be that 1 plus root x, so that part's obvious. But here's where we have to be a little circular. So we see that we have a dx that we're trying to replace right there. So what are we going to do to get dx over here? Multiply both sides. Or I guess I should do it maybe here. So dx is going to be 2 root x du, right? So, okay, but we can't have u's and x's inside here. So what can we do about that root x?
That's the x with what the u sub is. Again.
So if we look at the u sub up here, we can take that and isolate root x. We kind of did this earlier with one problem. So root x we see is u minus 1, and we can substitute that in right there. So that's going to be, kind of circular substitution where we take the substitution step and then isolate for part of it and then substitute it in there. So this whole dx now is going to become 2 multiplied by u minus 1 du. Now we're okay. Now we have limits of integration to deal with too. But now we have everything with u's. So that's kind of what our target was. But a little bit feels a little sneaky.
We didn't translate the range.
So we're going to do that. So when x is 0, what is u equal to? 1. And when x is 1, u is 2. We've got that. So let's go ahead and expand. So that 2 can certainly pop out to the front as a coefficient. And then we have u times u to the half, so that's u to the 3 halves. And then square root of u times 1, that's just u to the half du. All right, so we have 2 times, this looks like one of the ones on the exam also. So that's u to the 5 halves times 2 fifths. And then integrating u to the half, that's u to the 3 halves times 2 thirds. That's going to go from 1 to 2. Plugging in the 2, so that's square root of 2 5 times. Square root of 2 5 times, if you have 2 of them, root 2 times root 2 is 2. So we're going to have 2 times 2, which is 4, times root 2. So we're going to have 2 fifths times 2 root 2. Minus 2 thirds.
4 root 2.
Oh, 4 root 2. I said it, right?
Yep.
I think I said it.
You did.
Come on, hand. And then 2 thirds multiplied by here is 2 root 2. So we've got that. All we can do is simplify this a little bit. So we're going to have 2 distributed, so we'll have 16 root 2 over 5. Oh, I guess we're going to have some more. That's going to be 4 times 2 is 8. Let's see, 4 times 2 is 8 over 3 root 2. Combine those, so 3 times 16 is 48. 48 minus 40 is 8 root 2 divided by 15. So sometimes we'll have substitutions that have that circular kind of weird feel to them.
And you missed the subtraction by 1, correct? Plug in for 1.
Say that again?
You missed the plug-in for lower bound.
I totally forgot to plug in the lower bound. It's not 0.
It's not 0.
It's not 0.
It was 0.
So there's the upper bound. Let's back off that square then. So this is the upper bound. If we subtract off the lower bound, we're going to get minus 2 multiplied by, plugging in a 1. 1 to the 5 halves or 1 to the 3 halves is 1. So we'll have 2 fifths minus 2/3. So let's get caught up over here. Sorry, you're not done. All right, so there's that top part, and then down here, if this is going to be 6 minus 10, which is negative 4/15, times negative 2 is positive 8/15. All right, so then we have 48 minus 40. 48 minus 40 is 8 root 2 plus 8 all divided by 15. There we go.
Back up the top.
Yeah.
I'm going from U's to right there.
Yep.
So how you get to U to the 3/2?
So if we take u to the 1/2 times u to the 1, u to the, when we have the same base, we add the exponents, so 1 plus 1/2. 1 plus 1/2 is 3/2.
So when you're, okay, so you have square root of U is U to the 1/2 plus 1.
Yep.
And then where are you getting the U to the 1/2?
I'm the negative one.
So then times the negative 1. So then this square root of u gets multiplied over here. So that's u to the
I got
1/2
it.
times
You're
1.
factoring in the square root of U. Okay.
Yeah.
And then the 2 just goes out to the front.
Out to the front.
2 jumps. 2's like the puppy dog, wants to be in front. All right, one more oddball one. This section is just hard because it's all over the map, different techniques with random kind of one-off scenarios. Integration by parts is going to be much more linear in nature, much more forward, not all web-like. Okay, so this says think of the power reduction identities. Let me just go grab this power reduction identity for a second. So let's take that power reduction identity. Let's put it over here. Is it not going to let me paste you? There, paste. All right, there it is. Okay, so this looks, get off there. So it looks a lot like it. If you focus your attention on this numerator right there, that looks like what's inside the square root. And so what we're going to do here, the quote-unquote the trick, if we isolate this 1 plus cosine, if we try, 1 plus cosine of 2 theta, do you agree that we could write it like that? All right. Well then, if we take our original integral, we can make this the integral from 0 to pi over 2 square root of 2 cosine squared of theta. So there is a homework question that uses this technique where we take a power reduction identity and kind of rewrite it. Because now we're almost there. What do we do next? No u sub. Simpler.
Simplify the
Simplify, so that's square root of 2 times cosine. D theta. And then what's the integral of cosine?
negative sign.
Positive sign. You get that. Sine of 0 is 0. Sine of pi over 2 is 1, so we get root 2. So that's kind of a strategy. Now let me ask you this related question, see if I can draw you off sides. So what if we had, I shouldn't have said that, right? Now you're looking for it. What if we had a slightly different scenario? What if our interval went from pi over 2 to pi? what would be the next step? So we're going pi over 2 to pi. What would the next step be here? Certainly square root of 2. How about square root of cosine squared? Negative cosine of theta.
Oh, I get it.
Negative cosine of theta, d theta. Because the square root of x is not always x. The square root of x, the square root of x squared is not always x. Let's write it up here. The square root of x squared is not always x. The square root of x, it's being a little finicky. The square root of x squared is absolute x, which is a piecewise defined function, equal to x if x is greater than or equal to 0, and it's equal to negative x if x is negative.
Cosine is negative.
Square root of x squared is not always x. It depends on whether x is positive or negative.
But cosine is negative for those values.
So for these values of theta, cosine is negative, right? In quadrant 2, pi over 2 to pi, I guess that's over here, pi over 2 to pi, cosine is negative. So we would have a slightly different answer here. So we get negative root 2, integral cosine is still sine. And then we would have to plug in these values. Sine of pi is 0. Sine of pi over 2 is 1, so it's going to be 0 minus a minus, so it's going to be plus. Oh, we end up with the same answer anyway. Not always the case. Sine of pi is 0, sine of pi over 2 is 1.
If it were, say, 0 to pi, would you need to do two different?
Yep,
Okay.
exactly. Then you'd have to break it apart. Then
You'd
you'd
have
have
to
to
split equal.
piecewise break it apart.
Okay.
Okay, so, yeah, this is important. Important algebra that's often overlooked or forgotten about. Yeah, no problem.
Security. Time to go home yet? 20 minutes. My brain is not that already. Yeah.
Zach, bring your phone. Bring your phone.
Wait, is there anything wrong?
Sad. Okay, so our next technique, one of the most important integration techniques there is integration by parts. And so integration by parts, first off, it's so important because we are going to be able to integrate inverse trig functions. We're going to be able to integrate the log function. A couple of you thought you knew how to integrate the log function on the exam.
Might have been me.
You might have been one of them. We do not know the integral of natural log. You know the derivative of natural log. The derivative of natural log is 1 over x. You do not know the integral of natural log yet, but we will get to it very soon. So this technique is super cool because we are going to be able to integrate some functions that are just way more complicated. Now, and kind of obscure functions like the natural log and inverse trig functions. What I want you to think about when you hear integration by parts, you should think of it kind of like a reverse product rule. So you know the product rule for derivatives, and integration by parts is going to be like a reverse product rule. All right? So when we look at this, this is going to be much more classic where we have a product right here, and our integration by parts is going to be able to find an antiderivative for a product. Now when you look at these other kind of oddball ones, you don't see a product there, but this technique will work even if you don't have a product in some cases. But the primary function of the integration by parts technique is a reverse product rule. All right, so let's take a look at how it how it is implemented. And when you see this, I'm referring to that as a product too, right? Division is the same as multiplication. If you have 2 over 3, it's 2 times 1/3. So that's a product. All right, so we can think of this as x times 1 over the square root of x plus 1. All right, so here is how integration by parts works. It's going to look like this, and we are going to need some sort of memory aid in order to remember that formula because it's not obvious. And this is where we, and I'm sure many of you have already heard this expression, ultraviolet voodoo. So on the right-hand side, UV minus VDU, there is the ultraviolet voodoo. So it's UV minus the integral of voodoo. Ultraviolet voodoo. Good luck, Zach.
It's nothing I did wrong.
What's that?
It's nothing I did wrong.
Oh, no, I know. I hope your mom's okay. Good luck. So that's where this acronym or word thing comes from, ultraviolet voodoo. So the right-hand side, UV minus integral of VDU. VDU is the voodoo, UV is the ultraviolet. Makes it pretty easy to remember that. Most students don't have trouble remembering that with that little word trick. So here is the idea. What we have to do is take this UdV and identify a U and a dV from within the integral we're trying to evaluate. So we need to identify something as U, identify something as dV, and then from the U, we will find du, its derivative, and from the dV, we will find v, its integral. So here's how we're going to do this. So we are going to set up a little table, integration by parts table. So we're going to build a U and we're going to build a dV. So this is what we have to separate our integrand into. Obviously, the dx has to come over here. The dx has to go with the dv somehow. And then this, the choices here can be complicated. You could put x right here. So you could put the x right here, and then you could put the rest of it over here, the dx over the square root of x plus 1. You know, you could put 1 over square root of x plus 1 here, and then x dx over here. You could do it in many ways. And there's not a great rule of thumb for what works best. My advice is to put the biggest part that you can integrate, because over here we're going to integrate, over here we're going to differentiate. We're putting dv here, and we're going to build v from dv by integrating. And over here we're going to build du from u by differentiating. So the integration is always harder than differentiation. So if we can pick apart this and get the biggest chunk that we can easily integrate, that's usually the best strategy. All right, so obviously if we put the x over here, we can integrate that really easily. But what about if we did this part? If we wrote this as, let's write it with a 1/2 power. Isn't this pretty easy to integrate?
Yes.
So if we did that, right, we could just move it into the numerator and then just do our add 1 and divide by the new exponent business. All right, so if we think about coming off to the side, if we wanted to integrate that, we would say, oh, well, let's write it with a negative exponent, dx. That's linear, so all we do is add 1 to the exponent, divide by the new exponent, and then do reverse chain rule, but reverse chain rule is just division by 1, so it doesn't do anything. Okay, that's bigger than integrating just x. If you can take the biggest chunk and integrate it, usually that's the best strategy. So we integrate that, we're going to get our v will be 2 square root of x plus 1. Here, you might say, oh, what about the c? It doesn't matter what you pick for c, so we will always pick 0. It will not matter. You can pick whatever number you want. 0 works just as well as any other number, so we will always pick 0 with integration by parts. We'll always do that. Okay, so we're starting with u and dv, and then we're going to build the bottom row. So we start with the top row. So now that means that u has to be whatever's left. Okay, the only thing left was the x. All right, so this quantity here multiplied by this quantity here, that is the integrand. It's what's inside the integral with respect to x. Okay, so then we differentiate this side, and the derivative of x, we get dx. So there is our integration by parts recipe. We've got all the components, all the ingredients for this integration by parts, and then there is our formula, uv minus integral of v to u. So our integral becomes uv. uv is this main diagonal right here, u times v. So u times v is going to turn into x multiplied by 2 multiplied by the square root of x plus 1. So there's uv minus the integral of voodoo. Voodoo is the bottom row. Voodoo is right there, the bottom row. So v du is dx. So there is our rewriting. So there is uv minus the integral of v to u. Ultraviolet minus integral of voodoo. And once again, we know how to do this integration. So we have this part out in front. And we can do this integration regular power rule. So this is going to be minus 2. We take our x plus 1. We add 1 to the exponent to get 3/2. Multiply by 2/3. Divide by 3/2, multiply by 2/3. Either way, same. So there is our final answer then. So we get 2x square root x plus 1 minus 4/3 x plus 1 3/2 plus c. So this technique takes practice. So we need to, get this formula into our heads, muscle memory, and the hard part, of course, is identifying u and dv. But again, the best strategy, in my opinion, try to get the biggest chunk that's integrable. That's usually, almost always, that's enough. So let's try another one. Okay, well, let's do these two first. This is why? Because we've wanted to know the integrals of these for a long time, especially that one. Okay, so let's go with our little table, our recipe here. We need a u and we need a dv. So those two come right from the integrand there, and we want to pick dv to be the biggest piece that's integrable. Well, we can't put the inverse sign with the dv because that's what the problem is already, to integrate inverse sign. So what we're going to do is this. We're going to do this right here. Okay, so we took everything in here and moved it around. dv is the biggest part that's integrable. Well, the dx always has to go with the dv, but we only have one factor here, inverse sine, and it can't go there because to get to v we have to integrate, and we can't integrate inverse sine. Not yet. But we can differentiate inverse sine. Inverse sine's derivative is 1 over the square root of 1 minus x squared dx. And if we integrate this, we get v is equal to x. And now we're ready to do our ultraviolet voodoo. So we do the main diagonal minus the bottom row. So uv, that's the ultraviolet. That's going to be x inverse sine of x uv minus the integral of the bottom row, voodoo, x over the square root of 1 minus x squared dx. And what technique do we use for that? U sub. If we let u be what's in the root, we have a quadratic in the root, and the derivative of a quadratic is a linear. So the u sub is going to work perfectly here. So we get du equals minus 2x dx. Let's isolate the x dx. So our integration will become let's see, so x dx is du over negative 2. So the over negative 2 comes out to the front. That's going to make it a plus 1/2. And then on the inside, we're going to have u to the minus 1/2 times du. Yes, I know, we already used u to represent inverse sine. This u is different, right? We're using u for u sub and u for integration by parts. Yeah. Okay, so add 1 to the exponent and we get positive 1/2. We're going to divide by positive 1/2, which just cancels out the 1/2 that's already in front. So we're going to have 1/2 multiplied by 2. So u to the 1/2 divided by that. Okay, so u to the 1/2 is square root of u. And all we have left to do is substitute our u back in. And we see that the u is 1 minus x squared. So here's our final answer. So that is the antiderivative for inverse sine. Not something anyone would ever memorize. Not necessary.
Where are you getting u to the 1/2? Negative 1/2 again? Go back up.
Yep.
When you're,
So the u to the negative 1/2, this u is in the bottom, right?
yep, okay, so it's up top.
So it's u to the 1/2 in the bottom, and if we move it upstairs, we switch it.
Okay.
We switch it. Now the one that you're going to see much more frequently, integral of natural log, it's so tempting to say that it's 1 over x. It is not 1 over x. The derivative of 1 over x does not get you back to natural log. Right? In antiderivatives, derivatives should get you back to where you started. So, all right, so here's what we're going to do. Same idea. We're going to do a u and a dv. And we're kind of in the same boat that we were in the last one. We know the dx has to go over here. And we can't put the natural log over there because then we're, trying to do what we're trying to do already. So natural log of x is going to go over here. And then du will be 1 over x dx, because the derivative of natural log is that. And then we integrate over here. And so here's where we're at. The integral of natural log of x dx is u times v. U times v is x ln x, uv, minus the integral of v du. And what is v times du? Just 1. V times du is 1 dx. So we're doing the main diagonal, and then we're doing that. So 1 over x times x is 1. Integral of dx is just x. And here is that antiderivative that we were curious about. So this is the antiderivative for natural log of x. Let's check. So x ln x minus x. So if we take the derivative of that, if we have x ln x minus x plus c, and we take that derivative, let's see. All right, well, first, the derivative of this is a product rule. So it's first times derivative of second plus derivative of first times second. Everyone okay with that product rule? First derivative second plus derivative first times second.
Just equals ln x.
And so what's the derivative of negative x?
Negative 1.
-1. Derivative of c? 0. And then what is x times 1 over x? 1. So this and this cancel. So we are left with ln x. So that proves to us that this is in fact the general antiderivative for natural log of x. X ln x minus x. Okay. Now Zach had asked earlier about repeated U substitution. One thing you are going to see not infrequently is repeated integration by parts. It's not uncommon to get this second integral to be in a case where you need to use integration by parts again. So that's not going to be uncommon. But we'll usually restrict it to just twice max in here. All right, let's go ahead and stop there. Anyone have questions on their test? You can hang around. I can answer them. Lincoln? Oh, yeah. So there's a shortcut technique called the tabular method, which if you had to do it like 6 times in a row, you can set up this. You can kind of see the pattern where we're differentiating here, integrating here, and if you have to do multiple times, you can set up this big table, and there is a way.
But you would not be uncommon to have to do it. Not
We'll see kind of the pattern that leads us down that rabbit hole. All right, week 5 has begun. Right?
Yeah.
At the end of this week, we're a third of the way through. And remember, eye on the prize, you're to become an integration ninja this semester. So get practicing. Integration ninjas. Takes a lot of practice. See you all on Thursday.